have our second last lecture in the area of free electrons. So remember that these electrons are non-interacting. They obey the Fermi-Dirac statistics. So they are called a Fermi sea of electrons. And we looked at certain properties of these electrons. At the moment, we are right in the midst of seeing how these electrons respond to a magnetic field. So in the previous lecture, we calculated the density of states for these electrons, and we observed that the density of states does indeed change upon the application of a magnetic field. The next question is whether the Fermi energy changes. We know that the Fermi energy changes with temperature, for example. There is a weak dependence. What is the dependence of the Fermi temperature on how does it respond to magnetic fields? And in the process, we look at magneto-oscillatory phenomena. And we'll reserve some of these phenomena to the homework problems in homework number 7 as well. So far we've looked at the density of states. In the absence of a magnetic field, the density of states, of course in 3D, it follows this square root relationship. And in the presence of a magnetic field, the density of states kind of rides on top of these are spikes on top of the native curve for a 3D solid. Correct? And we also rescaled the energy and wrote this down in terms of x, where x is whatever the energy we have divided by Planck constant into the cyclotron frequency. So, and we were able to write down these density of states in terms of x. So the density of states in the absence of a magnetic field is given by over x naught, so T at EF and x. So this is one density of states where DEF is the density of states at the Fermi level. And when I write EF, it means the Fermi energy in the absence of a magnetic field. Okay? So this is a curve for this scenario, and the curve for this scenario is given by a summation of square root functions as they appear in the denominator. So in the presence of a magnetic field, the density of states is given by DEF, a very similar prefactor, only that we have a factor of 1/2 and a summation that goes from L goes from 0 to some maximum value L max x minus L plus half. So this was the main subject of our lecture on yesterday. So plots of these densities of states are given here. All right. So this is where we finished our previous lecture. Now, how is this useful? And okay, so we have the density of states in the presence of a magnetic field for these electrons. So how is all of this of any use to us? So the next question is, how can we calculate the energies in the presence of a magnetic field? The energies we do know, generally they are given by the total energy, for example, is an integral over an energy variable with the density of states function and the energy variable itself from 0 to some Fermi level. So this is the density of states at 0 kelvins. Now what will happen if we insert the density of states in the presence of a magnetic field? Not only would this density of states be replaced by this functional form or this functional form, this upper limit to the integral will also change. So we have found the density of states in the presence of field. Let's now try to investigate how are we able to find out the Fermi level. Okay. So if this is the Fermi level in the absence of a magnetic field EF, this is our EF. In the presence of a magnetic field, this Fermi level can shift, right? In either way, in either direction. Okay, so a new Fermi level is set up. Suppose that Fermi level is EF plus some change in the Fermi level, delta EF. Okay, so we want to find out how does the Fermi level change at a certain magnetic field. So in order to find out the changes in the Fermi level, we have to resort to another concept which is called the integrated density of states. So what happens, by the way, if I just integrate the density of states? So what would this integral look like without the E? What would be the dimensions of this integral? The number of electrons, the number of states that are available to the electrons. Okay, so integrating the density of states is useful. Now you apply a magnetic field, the number of states shouldn't change, the number of electrons don't change. So that's why a next step in this calculation is finding out an integral to the density of states. So let's calculate the integrated density of states, and once you integrate the density of states, you get the number of electrons, which of course is a dimensionless number. Okay, because the units of this dE are number of states per unit energy, and you're integrating with respect to energy, you will get the number of states. If you predefine your density of states per unit volume, you will get the number of states per unit volume. Okay, so now let's calculate the integrated density of states with and without the magnetic field. And in that process, we aim and hope to find out the changes in the Fermi level. So let's move on to the integrated density of states. Okay, so if I integrate, first of all, in the absence of a magnetic field, if I take dE and integrate with respect to energy, the Fermi level is EF. I will of course get dE. Let's denote this integrated density of states by density of states with a tilde sign. And I know this is going to be equal to the number of electrons. Now I'm going to use a specific density of states, number of states per unit energy per unit volume. So the integral is going to be the number of electrons per unit volume. Okay. So any confusions about this? This should be true. Now if I change the variable from E to X, this is what this thing looks like. H bar omega c dx from E0 to x naught, where x naught is EF over H bar c. So this variable is EF over H bar omega c. Correct? This H bar omega c is factored out because this energy is x into H bar omega c. So this becomes equal to H bar omega c dx. I already have an expression for dx over there, d EF x naught square root x raised to 1 by half. This becomes h bar omega c d e f. Let's first of all try to find out this value at arbitrary x. Okay, so let's just keep this at e at the moment. Okay, let's take the upper limit to be e. Got it? So this becomes h bar omega c d e f x naught x 3 by 2 into 2 by 3. Yes. So this becomes d bar as a function of x, h bar omega c, d e f is some scalar, x naught h bar 1 by half, there's a 2 by 3 here, and I have x 3 by 2. Okay. So this is my integrated density of states in the absence of a magnetic field. Yeah, it is equal to the states that exist up to a certain energy level. The number of states that exist up to a certain energy level. If this upper limit is equal to the Fermi energy, then it becomes the total number of states. So of course, this integral is a dimensionless number which corresponds to the number of states up till a certain level. Okay, so I want to re-rationalize this h bar omega c and write this in terms of energies. So I can write this as h bar omega c can be written as E over x as well. Okay, so let's check. Can we check that this, when the upper limit is x equals x naught, this must give us the number of electrons. I can check, right? So if I put this x equals x naught, this expression should give me the number of electrons because it is an integrated density of states. So if I integrate right up till the Fermi level, I get the number of electrons. So this becomes 2 over 3 h bar omega c d e f x naught raised to power 1 by 2. This becomes x naught raised to power 3 by 2. So this becomes x naught. X naught into h bar omega c is EF. Right? So this becomes 2 over 3 h bar omega c x naught. X naught is, sorry, yes, x naught. X naught is sorry, DEF, and this becomes x naught. Now x naught into h bar omega c is EF. So this becomes 2 over 3 h bar omega EF, but D over EF we've already calculated from our previous lectures, 3 over 2 into n over EF. This is DF. This thing DEF is 3 over 2 into n over EF from a prior lecture. Hence, the result is indeed n. So the integrated density of states, we've checked that when the upper limit is equal to the Fermi level, the integrated density of states is indeed, in the absence of a field, equal to the number of electrons. So So the integrated density of states is proportional to x is for 3 by 2. We can plot this as well. Let's now plot the integrated density of states in the presence of a magnetic field. For that, we'll have to integrate this equation. So let's call this equation number 1, equation number 2. This is our equation number 3. So if I integrate equation number 2, I will get D in the presence of a magnetic field, integrated density of states, which is half dEf over x naught square root. The summation sign, we know what L max is. Now we want to integrate, an h bar omega c factor appears, integrate with respect to x from 0 now to some upper limit which is still x. Okay, some upper limit x, and we are left with x minus L plus half minus half. So we need to find out this integral. It's pretty simple. It's just an integral of an reciprocal square root function. So in the presence of a magnetic field, our integrated density of states becomes half dEf x naught square root h bar omega c integral x minus L plus half raised to power 1 by 2 divided by 1 by 2. Okay, this is how this integral is evaluated. Okay, so this half simply goes away, and I'm left with this expression. Okay, so this part seems to be very similar to the part that we have over here. So this part here is exactly similar to this part. Okay, there's an additional factor of 2 over 3 over here. The functional form is given by x is power 3 by 2, and here it's given by a summation over square root functions. So this object really is equal to x minus 1 half plus x minus 3 by 2 plus x minus 5 by 2 up till some x minus L max by 1 half. Okay, and L max is determined by the Fermi energy, which changes very slightly by the application of a magnetic field. Okay, so you want to plot this. This is equation number 4, and we want to plot this together with equation number 3 and see what the plots really look like. So can you make a prediction for how, if you were to plot with respect to x naught, this is, sorry, with respect to x, dx integrated, what will this plot look like? We plotted the density of states. Now we're going to plot the integrated density of states. So on the y-axis for the integrated density of states, you have the number of electrons, right, up to a certain level. Now this is,
सर कल भी कॉन्केव भी हमने बनाया था, तो अगर हम कंपेयर करें इनके
एक स्क्वायर रूट है, this one is raised to power 3 by 2. Instead of 0.5, the exponent is now 3 over 2 or 1.5. Okay, so let's see. So this is from yesterday, the density of states in the presence and absence of a magnetic field, and both of them juxtaposed together. This was where we finished our previous lecture. So now let's move on to the integrated density of states. So I'm ignoring the common factors in both, just a coefficient. So this is the integrated density of states in the absence of a magnetic field. Got it? It's a positive going function. It's actually convex. Now I plot this together with the integrated density of states in the presence of a magnetic field. Now on this graph you can see a blue curve, which is just this curve, and on top of it there's another curve that is riding, which is slightly non-monotonous. It's non-monotonous, non-monotonic. It's kind of going down, then going up, so it's humpy. And there are humps at 1.5, 3.5, sorry, 2.5, 3.5, 4.5, and so on. It has all of these humps starting from 0.5. 1 by 2, 3 by 2, and so on. You see, 1 by 2, 3 by 2, 5 by 2, 7 by 2, and so on. So if I zoom in a little bit, this is what this integrated density of states looks like in the presence of a magnetic field. It has lost its monotonicity, it's discontinuous, there are cusps over here. Okay, but still it follows the same general trajectory as the original, but the quantization due to the magnetic field, which is called Landau quantization, shows up not only in the density of states but also the integrated density of states. And this already tells us that the Fermi level is now going to change in the presence of a magnetic field, and I'll show you how. I'll make an argument for that. And this is the same curve, kind of zoomed in a little bit. Okay, so now let's look at our argument. Please turn on the lights. Let's look at our argument for the change in the density of this is d integrated x, and in yellow okay, so this yellow is dbx integrated. Now suppose in the absence of a magnetic field this is my Fermi level x naught. Since I have made the variables dimensionless, instead of energy I have x's, and this corresponds to the Fermi level EF naught or EF over h power omega c. So this is the Fermi level. Now if I look at the white curve in the absence of a magnetic field, this point here, what should this correspond to? What should this ordinate correspond to?
Oh, it's something.
Yes, so this corresponds to the number density of electrons. The integrated density of states at x dot at the Fermi level must equal to the number of electrons, which is this thing when x becomes equal to x naught, and then all of this becomes equal to this n. That's what we've shown analytically. So in this graphical representation, what we do know is that this point must correspond to n. Okay, Now, in the presence of a magnetic field, n should not change. So for the yellow curve, we want to find the projection on the energy axis which has the same ordinate, which has the same number of electrons. And that projection, so if you see, where does the yellow curve have an ordinate equal to n? It's this point over here. And if I make a projection downwards, this point here would correspond to the Fermi energy in the presence of a magnetic field. Correct? Because for the yellow curve, the integrated density of states, we want to keep that the same, which means that we want to keep d, b, x, at some new Fermi energy in the presence of a magnetic field xb, we want to keep this equal to the density of states at x naught, integrated density of states at x naught, and we want to keep both of these integrations equal to n. Correct? Because the number of electrons is not changing. Okay, so hence this point is the new Fermi energy in the presence of a magnetic field corresponding to this Fermi energy in the absence of a magnetic field. So this is our xb. Alright, got it? So the Fermi energy has slightly shifted. The Fermi energy is now some x naught plus some change in the Fermi energy, delta x, imposed by the application of a magnetic field. Yes? It's apparent from the graph.
What would that mean?
So sometimes the Fermi energy goes down, sometimes the Fermi energy goes up. If I choose another point, suppose this were my Fermi energy, x naught. If this were my Fermi energy, this is my number density of electrons here. This would be my new Fermi energy in the presence of magnetic field. So for in this case, delta x is positive. The Fermi energy has gone up. So you want to keep the area under both curves. So you don't want to keep the area under both curves. You want to keep their ordinates the same because these are integrated density of states. Okay. So the Fermi energy is oscillatory. It sometimes goes beyond the Fermi energy in the absence of magnetic field and sometimes goes smaller than it. It's oscillatory. Now how do you find this delta x? In fact, by drawing the graph, you can follow Alhamdulillah, you can follow a graphical approach and find out what the delta x's are. But you can also do a numerical solution. This is the equation that you need to solve. So what you really need to do is you take this expression x naught plus delta x. This expression, so you replace this x with xb, x naught plus delta x, and equate this to d in the absence of a magnetic field. Okay, so what you really want to do is you want to equate equation number 3 and equation number 4 at a certain value of x naught. Suppose your Fermi energy in the absence of a magnetic field is x naught. So when that happens, so this becomes, so if I then equate equation number 3 with equation number 4, I will have 2 over 3 . So for omega c. So I just kind of ignore the parts that are common. 2/3 x naught, this x naught 3/2. So for a given Fermi energy 3 x naught, this must equal sum over x naught plus delta x minus L plus half, where L goes from 0 to some L max. So you want to solve this equation. So you keep your x naught fixed. For a certain Fermi energy, you want to find out how much will the Fermi energy change when you apply a magnetic field. Okay, and this x naught is, remember, EF over h bar omega c. So where does magnetic field come into this picture? How is magnetic field taken care of in this equation number 5? It's no, it's in x naught, because x naught is EF over h bar omega c, and omega c is EB over m. So for a given magnetic field and a given Fermi energy in the absence of a magnetic field, so for example you place sodium metal which has a given Fermi energy and you place it inside a magnetic field of strength B. So you know what omega c is going to be and you know what x naught is going to be. So for that x naught, how much would the Fermi energy change for that particular field? That change in Fermi energy is delta x. So now you have an equation in which everything is known besides delta x. So you solve this equation numerically by some technique of numerical analysis. One possible technique is the bisection method. Other possible technique is the Newton-Raphson method. Any method that you fancy. You just solve this equation and find out for a particular value of x naught, which in disguise is inversely proportional to the magnetic field. For a particular value of magnetic field, you find out how much does the Fermi energy change. How much is delta x? Correct? So let me do this for you. Let me do this numerical kind of solution for you. So I take this equation and just kind of solve it. Okay, so how I do this numerically, I just recast this equation. So I want to find roots of L max x naught plus delta x minus L plus half, right? I multiply this by 3/2, divide by x naught raised to the power 3 minus 2 over 2, subtract 1 from this. So this, I find the roots of this equation. So finding the roots of this equation is tantamount to finding a solution to equation number 5. I just kind of do an algebraic manipulation. Okay, so I find the roots to this. This is nothing but equation number 5 written in a different form, which my computer program understands. So for a set of x naught, so what I'm going to do now, so this is the scheme. I take some set of x naughts, say from 0.1 to say 100. Okay, which is really choosing a set of b's, and if x naught goes high, it means the field is getting smaller. Small values of x naught correspond to larger fields. So for each x naught, I want to find out delta x. But I also need to find out what L max is going to be, because the number of Landau tubes is L max. If I have a different amount of magnetic field, the number of tubes is going to change. So the L max changes. And I know what the Fermi energy is. So I kind of find out L max. L max is such that L max plus half is less than x naught. Okay? Or h bar omega c into this is less than the Fermi energy. This is the constant. So for each x naught, I determine. So the first step is kind of make an array for x naught. The second step is make an array of L max. For each x naught, there will be a particular L max. Got it? And then I solve equation number 5. I find the roots to this characteristic polynomial. It's not a polynomial, but I find the roots to this algebraic expression. Okay, and this will give me, the solution to this will give me an array of delta x's corresponding to x naughts. So for each Fermi energy, for each x naught, for each magnetic field, I'll get some perturbation to the Fermi energy. Let's see how this comes out to be. Now from the graphical analysis, we observe that the Fermi energy oscillates between a positive and a negative value. The change in the Fermi energy is kind of oscillatory between positive and negative values. And the period for this change, which is this distance is the period in delta x naught is equal to 1 unit, which is just the step in the Landau staircase. Just L changes by 1 unit, everything kind of repeats itself. So the period of delta x should be equal to 1 unit. Got it? So Landau quantization is coming in its full glory. It's manifesting in different countenances, in different forms. So now let's try to kind of do this numerical solution. Let's run this algorithm and see what kind of delta x's do we get. Lights are on. So here x naught, let me increase the font size a little bit. Okay, nazar aa raha hai? Theek. So x naught is my sequence of fields. It's a table that goes from 0.1 to 100 in steps of 0.01. So I get approximately 1000 points. Then I kind of initialize an array for L max and put all zeros for the time being. Now I want to find out L maxes. So in the next step, I simply implement the algorithm. I put in the constraint on what L should, while L is less than L plus 1 is less than x minus half, I increment L. I keep on incrementing L until I hit the constraint. And then for that particular value of k, that particular value of the index, my L max is given by L minus 1, by the final value that I've hit. Okay, so for each of these x naughts, I calculate a table of L maxes. Each x naught will have one L max, 0, 1, 2, 3 and so on. Right? हाँ.
So जो आप constraint की बात कर रहे थे, वो change होती है या
This is the constraint, because The number of Landau tubes that is inscribed inside the Fermi sphere is finite. It's bounded on the upper side. You cannot have a very large number of Landau tubes. It cannot go on indefinitely. Okay? Because the Fermi sphere kind of restricts that. Everything inside the Fermi sphere is occupied. All the rest is unoccupied. Okay? So now I make this table of L maxes. And if you want to see your X naught is this table, right? Is this large table. These are your X naughts which correspond to your magnetic fields. And this really is your L max. Your first L max is 0, your 100th L max is 1, your 5 L max, the 500th number is L max is 5, and so on. So you get a sequence of L maxes. Now this equation roots, this is a table of delta x's. Here I am going to solve the numerical equation. Okay, and if you observe here, 3/2 into this summation divided by x naught is per 3/2 is exactly this equation. I have just put in this equation and find the roots of this. And I also have the Heaviside theta function which ensures that whatever goes in the square root is positive. Okay, so I get a table of roots, and xf is my change in the Fermi energy. Whatever roots I get, I just call it xf. Okay, so this dx is an initial guess. I think this algorithm uses the Newton-Raphson method. So I get my xf's. Okay, so first of all I find out the roots of the equation. I put that equal to xf. Now I want to plot. So now what I'm going to do, I am going to plot the xf's, the changes in xf's as a function of the magnetic field x naught. So I put x naught on the x-axis and plot the delta x's. समझ आ रही है?
सर ये बस मैथमेटिकल में फाइंड रूट बस एक फंक्शन जो चल जाता है पूरे इक्वेशन में
चल जाता है. हाँ, हर एक सॉफ्टवेयर में कोई ना कोई आपको कोई ना कोई कोड करना पड़ेगा ना, आपको रूट्स फाइंड करने पड़ेंगे ना.
नहीं वो बिल्ट इन बस वो डिफाइन कर लेते हैं. आई थिंक इस केस में वो dx या k को फाइंड करते हैं.
It's solving for dx, right? So it's solving for dx with initial guess 0. So here I plot. So here is a plot of the changes in the Fermi energy. Here I have x naught, and here is a plot of the change in the Fermi energy. So what I could also do is I can zoom in onto a small region to see what this looks like. Let me zoom in onto, say, a smaller region. So what's the length of my vector? I have 9,000 points, so let me go from 1 to 2,000, right? Here you go. So this is the variation in the Fermi energy, oscillating between positive and negative, exactly as I've described. And this period here, let me zoom in even further. Oh, sorry. Sorry. See, this is your delta x, the change in Fermi energy for a particular value of x dot. Got it? And if you observe, this kind of period is 1. This delta x naught is 1. So whenever the magnetic field changes such that this delta x is 1, I get the same behavior. And it's an asymmetric function. It doesn't have constant amplitude. There's slight asymmetry to this. So this is how the Fermi energy changes. Okay, and I can even, if I attempt to plot, so this is a change in the Fermi energy, I can attempt to plot the x naught. This is the overall Fermi energy. Now it's not dx, this is x plus dx naught plus dx. Now what I've done, this is my Fermi energy in the absence of a magnetic field, right? And it actually corresponds to the magnetic field. So this is my magnetic field, or the inverse of the magnetic field, and this is the overall Fermi energy, the original plus the perturbation. You see these slight kinks? Okay. So now this is the new Fermi energy. The Fermi energy does change slightly upon the application of a magnetic field. Now we have all of this. Can we turn on the lights, please? We have all of this in front of us. Let's try to calculate the energies. Any questions about this? The Fermi energy definitely changes. Slightly, albeit slightly, very minutely, but it does change. Yes, please. ये तो सिर्फ आपको इस कर्व से इन मैथमेटिकल फार्मूला से नज़र आ रही है. इसकी फिजिकल रीज़न मुझे नहीं पता, या फिजिकल रीज़न इसमें ढूंढना बहुत मुश्किल है कि, लेकिन जो आपको कर्व नज़र आ रहा है उसको एग्जैक्टली यहाँ डिपिक्ट किया गया. ठीक है. So let's move on to energies. Now, how do you calculate energies? So, just to give you a quick recap, if I take dx, dE and integrate this with respect to energy from 0 to EF, I will get the total energy, right, in the absence of a magnetic field. And I can put this in terms of x as well.
Just specifically, upper limit must be the Fermi energy.
Yes, because this is in the absence of a magnetic field. So this we've done already. This equals 3 over 5 n EF, right? This is the calculation we've already done. We can do this calculation in terms of x as well. You'll get the same result. In another form, this equals 2 over 5 E F square DEF. All right. So this is the energy in the absence of a magnetic field. We already know this. Let's call this U naught. Now, how do we find out the energy in the presence of a magnetic field? We simply take the density of states in the presence of a magnetic field and integrate with the new xb's that we've calculated. So now we have, for each x naught, we have an xb. So now the upper limit will not be x naught, it will be xb. So in the presence of a magnetic field, let's call the new energy ub, is going to be dE in the presence of a magnetic field E. But now this goes from 0 to EF plus the change in the Fermi energy. Now let's put everything in terms of h bar omega c and x. So this dE will give me an h bar omega c dx, right, from here 0 to xb, which we now have. We already have an array of xb's, which is x naught plus delta x. This dE, I can simply write this as dx in the presence of a magnetic field, which is equation number 4, which I can pick from equation number 4. And E is another x into h bar omega c, right? So I need to find out this integral. Got it? Very simple. So that I can find out the magnetic field, the energy in the presence of a magnetic field. So let's kind of move 1 or 2 steps further so that I can solve this integral. UB must equal h bar omega c whole square 0 to xb dx. Now dbx I just take from over there, def x bar square, right? Another h bar omega c dx sum over x minus L plus half. This is xb, x and another x. Correct? तीन दफा आएगा क्योंकि once it's coming from this term, E is h bar omega c, dE expressed, there is already another h bar omega c here and there is an E here as well. Okay, so when I compute all of this, so I compute h bar omega c whole square def ef x naught 3 by 2 L goes from 0 to L max 0 to xb dx x minus L minus 1/2. So this integral I've calculated for you over there. Okay, so now I know what my UB is going to turn is going to be. Okay, so if I calculate this UB, it's this expression is over there, so this becomes h bar omega c whole square def ef x naught 3 by 2 1 by 3 xb plus 2l plus 1, and I'm summing over l's, of course, I shouldn't forget that, L max square root of x minus L minus half and an additional factor of 2, which I've just taken as common. So this is my expression for ub. I already have an expression for u naught, which is this expression. Got it? So I have an expression for ub, I have an expression for u naught. Let's see what I would like to do next is I take my ub and see how different is it from the energy in the absence of a field. So I subtract from this u naught and normalize by u naught. Okay, so I form this expression. How much does the energy change by the application of a magnetic field? So this would be ub over u naught minus 1. So when I take this expression ub over u naught minus 1, I have all the ingredients in place. I just divide ub by u naught over there, and the result that I obtain is profoundly simple. It's simply 5 over 6 x naught 5 by 2 L goes from 0 to L max 2L plus xb, which is x naught plus delta x, which I've already calculated, plus 1 x naught plus delta x minus L plus half, all of this minus 1. So this is my fractional change in energy. I can plot this as a function of u naught. Okay, let's call this function wx naught. This will be some function of x naught, and let's see what this looks like. Any confusions? All right, so let's move back to our computation. So here what I've done, this is my wx. So as you can see, it's 5 by 6, this sum, right, with minus 1, so it has all the ingredients that I've written on the blackboard. I just plot it. I call this function f. On the blackboard I've called it w. So I compute this fractional change in the energy upon the imposition of a magnetic field. Now I want to plot. So here I plot, here I kind of make a table so that I can easily plot this, and next I plot. So this is what the function looks like. really nothing. So this is my x naught. So as we go from left to right, the field is decreasing. So when the field is small, this function is 0, so there is really no change in the energy. But all the action and the drama lies at large fields. X naught small, means large field. So let's zoom in onto this region and see what it looks like. Okay, so I kind of zoom in onto this large field region and plot the zoomed in part. This is what the zoomed in part looks like. The energy kind of oscillates as a function of the magnetic field. This is a magneto-oscillatory phenomenon. So the energy is now a periodic function of the magnetic field. Got it? I can zoom in onto this a bit even further. Here is a more closer look at the high field region. The energy is showing an undulatory behavior, an oscillatory behavior. These oscillations are called de Haas oscillations. De Haas oscillations. Van Alphen de Haas oscillations. So this is a real magnetic field oscillatory behavior that you observe. Now what you could do is you could do multiple things. So this is my Wx, right? And if I look at my Wx, this Wx is showing a decaying behavior. Okay, so I can find a closed form expression for this Wx. So let me kind of do the steps that are needed to highlight this. उम्मीद है हम 15 मिनट चुरा लेंगे. So this is my Wx, Wx naught. So x naught, Wx naught. We see that there is these oscillations riding on top of a decaying function. Now if you look at the average of these oscillations, forget about the oscillations for a minute. The proposal is that the mean value of these oscillations, the proposal is that Wx naught is some constant divided by x naught square. So it's a decaying exponent, is a decaying parabola. As x naught goes large, the average value of these oscillations drops as 1 over x naught square with some constant proportionality alpha. Okay, so let's see if this is a valid behavior. So what we would like to do is we would like to plot W with respect to x naught square. If we plot W with respect to x naught square, and if we get a straight line, this would be a valid assumption. So this is an ansatz in a sense. If we plot W, this W that we've just plotted with respect to x naught square and we got a straight line, then this would be a good ansatz. So now the next step what I do is I plot W with respect to 1 over x naught square. So I take my W and plot with respect to 1 over x naught square, and indeed I do get a straight line. If I forget the oscillations for a minute, of course it's an oscillatory function, but if I look at the mean values, it lies on a straight line. So W is some oscillatory function into alpha over x naught square. And I can find the slope of this line, which is my value of alpha, by doing a fit. When I do a fit, here I do a fit, my slope turns out to be 0.105. This is my slope. My alpha is 0.105. So now what I could do is W x naught is alpha over x naught square, where alpha is roughly 0.105, and on top of this there is some oscillatory function, right? So let's call that oscillatory function 1 plus some q as a function of x naught. Now we want to find out what this q looks like. Now this q is not constant. You see that the amplitudes are changing with x naught. So this q x naught looks like a sine function, an oscillatory function, but its amplitude is being modulated by the magnetic field. It's like a frequency modulated function. So we want to see how this q x naught changes with x naught. What's the dependence of q x naught on x naught? What would I like to do? I would like to change the ordering of this expression a little bit. So what I would do, I would take w x naught, multiply this with x naught square, divide by alpha, and subtract 1 from this. This will be my q x naught, correct? So this will give me an estimate of my q x naught. I do this reshuffling. So what I would like to do now, I would like to plot this function. I already have w, I multiply this with x naught squared, divide by 0.105, subtract 1 from this, and see what the plot for this with respect to x naught looks like, and from that I try to predict what is my q x naught. How does q x naught depend upon x naught itself? So now I want to plot this function, which is my substitute, proxy to q x naught with respect to x naught, and see what it looks like. Okay, so let me try to do that now. So here I have done that already for you. So I take my w, multiplied with x naught square, divide by alpha, subtract 1 from this, and plot this with respect to x naught.
सर हमने अल्फा की वैल्यू कैसे डिटरमाइन की थी?
वो स्लोप से डिटरमाइन की थी, इसकी स्लोप से, इसको फिट किया टू स्ट्रेट लाइन एंड डिटरमाइन अल्फा, which is 0.105. Okay, so this is a form for qx naught, and this is with respect to x naught. So how does this qx naught vary with x naught? Of course, when x naught goes up, qx naught kind of amplitude drops, right? So I need to have some reciprocal relationship of qx naught with x naught. Okay, so let's try to zoom in to these oscillations a little bit further. Right, and I plot the zoomed in version. This is what it looks like. I zoom in a bit. Now I kind of propose that so the oscillations are some oscillatory function, but what we are interested in is looking at the envelope of this oscillatory function. And for this envelope I need to find out the peaks of this function. So it turns out that the peaks of this function vary as, can you turn on the lights please? So qx naught, I propose, this is another ansatz, by looking at the form of this graph, I propose that this qx naught is some oscillatory function of constant amplitude. Let's call it q bar. But as x naught goes up, the amplitude drops. This is what happens in, say, field modulated. It's a field modulated oscillatory function. You might have come across frequency modulated FM or AM signal. So this is like an AM or an FM signal. As the field goes up, as x naught goes up, this drops. So I put x naught, its square root in the denominator. The square root turns out to be a better fit than the mere reciprocal. You can try both and see which one is a better fit. And of course, there has to be some constant beta as well. So now if I were to take the slopes, I can take the envelopes of this function and plot with respect to 1 over x naught square root. I will get a straight line. Okay? If I were to get a straight line, the slope of that line would be beta. And that does indeed happen. So if I now, so this is the last time we're going to do this modulation for the lights. Now you observe in this QQ3, what I'm trying to do is I'm going to plot this function with respect to 1 over square root. And this is the kind of function that I obtain. And I can also do, I've actually done a more careful, in my code here, I found out the peaks and then I plot the peaks as well, and I fit the peaks and I find this beta function which is 0.5. So everything now works out. So overall, if I were to find out finally what my energy looks like, my UB, final results, UB, U naught minus 1 is Wx, but Wx is alpha over x naught square 1 plus Qx naught, but Qx naught is this. So I have alpha over x naught square 1 plus beta q constant amplitude oscillatory function x naught, right? So this would mean that my UB equals U naught plus U naught alpha over x naught square plus U naught over x naught square alpha beta x naught another x naught, so this becomes x naught is 3 by 2. So this is my final expression for the energy of these free electrons in the presence of a magnetic field, and alpha and beta have been found in a semi-numerical fashion. Beta is 0.5 roughly, and this is 0.105 roughly. And this is q bar, this is an oscillatory function of period delta x naught is 1, and it's a constant. This q bar x naught is a constant amplitude function, and all the amplitude modulation has been taken care of by these extra terms in the denominator, x naught 3 by 2 and so on. Now once I have the energy for these free electrons, I can find various quantities. First of all, if I take this energy, what I could do, for example, is I could place x naught equals EF, which is the Fermi energy in the absence of a magnetic field, over h bar omega c. But omega c is EB m. So I can express this x naught explicitly in terms of the magnetic field. So I can find an expression for ub in terms of the magnetic field, and I can plot it. Now one thing I would like you to do before the next class is, which is tomorrow at 10 o'clock, 11 o'clock, you have this energy, you can find the magnetization of this free fermionic gas of electrons. Due to the Landau quantization effect, we did find out the polyparamagnetism for these electrons, but this orbital motion of the electrons, the polyparamagnetism, remember, came out because the electrons have a spin and they see a magnetic field. Some of them raise their energies, others lower their energy. So there is a population difference between the spin up and the spin down electrons, and from that population difference you find out the magnetization. Now this is another effect. This is due to the Landau quantization of these electrons, which in a way is just the Lenz's law. You put a magnetic field on electrons and they start revolving in cyclotron orbits, and their magnetization is opposing the applied field. So you will observe that the susceptibility or the magnetization will now be opposite to the magnetic field for this effect, for this Landau quantization effect. Now what I would like you to do before 11 o'clock, take this magnetization, this energy. How do I find out magnetization from energy? Simple hint is that if I have a magnetization M, and I put it inside a magnetic field, with a minus sign, this will give me the magnetic energy, right? For a single spin, the magnetic energy is minus mu dot B, where mu is the magnetic dipole moment. So if I have a magnetized sample and I put it inside a magnetic field, this is the magnetic energy of that sample. Now from this expression, how can I determine, so if I know U, how can I determine magnetization? And I suppose these are isotropic materials, the magnetization and the magnetic field are either aligned or anti-aligned. So if I were to take the derivative of the energy with respect to magnetic field, I'll get the magnetization. How do you get, for example, if I have an energy, and from the energy we know is force times the displacement, right? How do I get the force from the energy? I take the gradient of the energy with respect to the force, or with respect to the distance, right? I take the gradient of the energy, partial u over partial x, I get the force. Exactly in a similar manner, I take the gradient or the derivative of u with respect to b, I'll get the magnetization. So take this u, find its derivative with respect to b, and you get the magnetization with the negative sign. You take the derivative again with respect to another b, once more you'll get the susceptibility. So this is a homework problem for you before, please try to do this before 11 o'clock. And what you observe is that the magnetization will show oscillations as a function of the magnetic field. Now all of this is kind of, I don't know if you can find all of this in this fashion in a precise manner in any book. At least I haven't come across this, so kind of you really have to rely on your lecture notes for this. But also I'm preparing a homework problem so that most of these ideas get further consolidated. So tomorrow will be our last lecture on free electrons, activity of electrons. How do they conduct electricity? What happens when you place that Fermi sea of electrons in an electric field? Of course, conduction happens if you're talking about metals. So what are the implications of the Fermi-Dirac statistics on conduction? And how is it different from the classical theory of conductivity in metals? Next week will be our last week, and we'll devote that to the band structure, where many of the shortcomings of the free electron model are resolved. Inshallah, see you tomorrow.